looking at this next thing, which is called integration by recognition. So we've got a few problems we're going to work through on that. Can be a little bit tricky, but let's focus on this and see how we go. All right. This method just allows us to work with functions that are a little more difficult to integrate by first differentiating a related function and then using that to help us to integrate. Okay, so looking at this first one here, we are finding the derivative of the function 5x plus 1 cubed. So to differentiate that, okay, we're using the chain rule, and so we would multiply the derivative of the inner part by the derivative of the outer part. Okay, so dy dx will equal 5, because that's the derivative of the inner part, multiplied by the derivative of the outer, which would be 3 times 5x plus 1 squared, okay, which is going to simplify to 15 times 5x plus 1 squared. Okay, notice that we are then looking at part B, which says use this result to deduce the antiderivative of this one here, which you can see is very similar. The only difference here is a factor of 5. Okay, so for part B then, we're going to just go straight from this previous derivative down and say, well, if that's the derivative, then we can say the antiderivative of 15 times 5x plus 1 squared with respect to x will be what we started with, which is 5x plus 1 cubed, and of course we're going to put a plus c on the end. Okay, so we know that to be true because we differentiated first and then we've just gone backwards to get the antiderivative of that function, which takes us back to the original. However, we're wanting the antiderivative of 3 times 5x plus 1 squared, not 15 times 5x plus 1 squared. Okay, so what we can do then is we can look at this 15 and think, okay, let's just separate that out, basically going back to this part here. And we can take this 5 out the front, multiplied by 3 times 5x plus 1 squared dx. That must also be equal to what we've got here of 5x plus 1 cubed plus c. Now, can everyone see how this really is the same? Because all we've done is change this 15 into 5 times 3 and removed that 5 outside, which we know is a property of integrals that we can do. We can take any constant term that's being multiplied by a function and take it to the outside of our integral. What we want to do now is actually just get this part here on its own, because this is 5 times that. Well, we can divide both sides by 5. So if we divide both sides by 5, then we're going to end up with, on the left-hand side, the integral of 5x plus 1 squared dx, and that's then going to equal all of this divided by 5, or we could be the same as going 1/5 of 5x plus 1 cubed, and we could just change this to d, if you like, just a different constant term, where d is equal to c over 5. Okay, so I mean, you could leave it as c over 5 if you want, but or you could just even ignore the previous c's and just add it on at the end if you want, because it's just a constant term. Okay, so everyone okay with what we've done there? Okay, that's kind of the principle behind this process of integration by recognition. All right, let's have a look at then the next one here. Similar sort of idea. We're going to start by differentiating e to the x cubed. So dy dx. Okay, again, function of a function, need to use the chain rule. So the derivative of the x cubed part first would be 3x squared multiplied by the derivative of the exponential part, which we know actually remains unchanged. So that'll be e to the x cubed. So that's our derivative. Then we use that to proceed to end up with this. So you can see the difference between these two is simply a factor of 2. So we'll start by going, that means the integral of 3x squared times e to the x cubed dx will equal e to the x cubed plus c. Okay, that's just taking what we've done and working backwards. Now what we want, then we just need to think, okay, what we actually want inside the integral is 6x squared times e to the x cubed, not 3x squared. So if we multiply both sides by 2, then we're going, that'll change that to 6x squared e to the x cubed dx, and that then becomes 2e to the x cubed plus d, if you like, where d is equal to 2c. Okay. And we're just going to continue then with these next couple, same sort of idea. First, find the derivative of sine 2x plus 1, and then use that to anti-differentiate 8 cos 2x plus 1. So, d dx of sine 2x plus 1. Okay. We need to multiply the derivative of the 2x plus 1, which is 2, by the derivative of sine, which is going to be cos. I'll just get rid of that 2 times, just change that to that. Okay, so it's fairly straightforward. And now what we'll do is use that to integrate. So that means our integral of 2 cos 2x plus 1 dx will be sine 2x plus 1 plus our constant of integration c. Okay, so where do we go from here? Yes. Okay, we just need to change that 2 into an 8, and we know we do that by multiplying by 4. Okay, so here we've got this one here. We want to differentiate log base e of 5x squared minus 2. So that's derivative of log base e 5x squared minus 2. Okay, so differentiating the inner function, that's going to be 10x multiplied by the derivative of the log part, okay, which would be 1 over 5x squared minus 2. So that's 10x over 5x squared minus 2. Okay, so our integral then of what we've just found, integral of 10x over 5x squared minus 2 dx will equal the natural logarithm of 5x squared minus 2 plus c. Okay, so what's the connection then between our integral that we have and what we actually want? Yeah, so what we can do is that 10 there we don't want inside here. So yes, we could effectively just divide throughout by 10 or multiply through by a tenth. Or we can think, well, we could just take that 10 out the front. So all of that's going to work. Okay, so that's effectively what we have. And then we want to get that by itself. So dividing then by 10. Okay, so x cos x is what we're looking to differentiate. So this is not an application of the chain rule, but instead is an application of the product rule. So product rule, we've got u and v, and so we want to go v u dash plus u v dash. Okay, so v is cos x times the derivative of u, which would be 1. Okay, so that's going to be cos x plus u, which is x, times the derivative of cos x, which is negative sine x. So we'll just change that plus to a minus then, and that becomes x sine x. Okay, so a little bit different, this one, because we can see we've got just an extra term. So it's not just simply a case of multiplying by a number or dividing by a number, but we're still going to start in the same way. Okay, so we can therefore say that the integral of cos x minus x sine x dx is going to be equal to x cos x. I'm actually just going to leave off the constant of integration for the moment. I might just add that one at the end. Don't know why that's there. Okay. All right, so, but we know that when we are finding the integral of separate functions, we can actually split that into two separate integrals. So let's go like this, change that to the integral of cos x dx minus the integral of x sine x dx. And we know that is still going to equal our x cos x. Okay, by splitting that up, then we can basically move things around on that equation. We want to get this integral of x sine x on its own, because that's what we've actually what we're trying to find. So effectively what we would get is if we rearranged it, brought that over to this side and then brought the x cos x over with the integral of cos x dx, then we can say that the integral of x sine x dx will equal the integral of cos x dx minus x cos x. Okay, and so we know the integral of cos x is sine x. So then we end up with sine x minus x cos x, and we can add our constant of integration on the end there. Okay, that makes sense. So we're still following the same procedure, differentiating our starting function using our product rule, so we end up with separate terms here. We can see in this that we actually only want the x sine x to be what we're finding the integral of, but still starting the same way. The integral of this must equal what we started with before differentiating. But we know that one of the properties of integrals is that if we have the integral of f of x plus or minus g of x, okay, then that is the sum of the two separate integrals. So that's integral of fx dx plus or minus, depending on what it is, the integral of g of x. Okay, so we're just separating it out and then isolating this one, which is what we really want here, and then just bringing this one over to the other side with that. Okay, so I mean, it would have been negative square root of x sine x equal to x cos x minus the integral, but then just multiplying throughout by negative 1 will reverse those signs, which is why this is positive and this is negative. Okay. All right, so let's... Yep. Oh, yeah, thank you for pointing that out. That's exactly right. Don't need it there at all. That's exactly, we don't need to worry about that. I kind of ignored that. That's probably why previously I underlined it. All right, so yes, exactly. We don't need the constant of integration. All right, let's go on and look at what we're working with here, the last example. Okay, first, this one here, we're just wanting to show this relationship between the left-hand side and the right-hand side, and then use the fact that that's equal to that to help us to integrate this result or this particular function. Okay, there's a couple of ways we could do it. A foolproof way of doing it is just actually to use long division. So what we're going to do here then is go, well, if that's the numerator divided by denominator, so let's say that's 5x plus 1 then, divided by x plus 1. And so we're dividing x into 5x, that's 5. And then we multiply, so 5 times x is 5x, and then 5 times 1 is 5. And then subtracting, the 5x's eliminate, and we get 1 minus 5, which is negative 4. And so we can use that result to then rewrite our 5x plus 1 over x plus 1. So the division is, we're left with 5 whole numbers, okay, so that gives us 5. And then we've got this remainder we write as minus 4 over our divisor, which is x plus 1. Okay. So that's how we can do it that way. I mean, the other way is you could think of it like this. Let's have 5x plus 1 over x plus 1. Now we can see that what we want here is just a 4 here and a 5. So what we can do is then change this positive 1 to 5x plus 5 and then minus 4, okay, over x plus 1. So your 5 minus 4 is still going to give you this plus 1, but we can split this up into two separate fractions, right? So 5x plus 5 over x plus 1 minus 4 over x plus 1. And we can see here we've got a common factor of 5, so you've got 5 outside of x plus 1 over x plus 1. That actually allows those two expressions, the x plus 1 there, to cancel out. And we're just left with 5 then. So that gives us 5 minus 4 over x plus 1. So that's another way you could work through that, which is perfectly legitimate. It's just an algebraic manipulation of those. Okay, so either of those is fine. All right, so we want to use that result, this result here, to integrate this. So what that means is because they're equivalent, we can say that the integral of 5x plus 1 over x plus 1 dx must be the same or equal to integral of 5 minus 4 over x plus 1. And so we've got two separate functions there that we can integrate. So the integral of 5 becomes 5x. And the integral of 4 over x plus 1, okay, is going to give us 4 times the natural log of x plus 1. And that's our result.
Why does it use straight lines instead of brackets?
Because as a function, log of x plus 1, the x plus 1 part has to be positive. Okay, and these straight lines representing the absolute value. So if you've got a negative value for x, then this will ensure that that whole thing becomes positive. Okay, so that's why. Okay, any other questions? All right, so exercise 9C will give you particular practice on integrating those different types.